Hello.
Hello.
Hello, Doc.
Please, yeah, can you hear me?
Yes, please.
Yes, please.
And you can also see my screen.
Yes.
Yeah, yes, Doc.
Yeah, can see.
Okay. Yeah. So okay, I guess we can start the 30 minutes past. Is that your number, or maybe Sam will be joining? Yeah. So you're only 10.
Doc, they will join when you start.
Oh, okay. So I should start. Well, so let's look at. I hope the course code is correct. If it's not correct, then I think you're on the wrong platform then. Okay, so electrochemistry. Okay. Yeah, so as we agreed, so we meet today and then Friday, is that correct?
Yes, Doc.
Okay. Friday, same time, 5 or the 5:30 should be okay. Okay, so let's look at some things. Now we're looking at yeah, hello. It's raining here, so I don't know whether that's the issue
Yeah.
there. It's not stable at all. Okay, so I was asking you if you did CAP 203.
Please, Doc, we don't know that course. I don't
That's
is it, mhm.
physical chemistry one. You
Yes,
did do
please, we do.
yes. So in that physical chemistry one, we did some in field of studies like thermochemistry, chemical kinetics, then electrochemistry. Is that correct?
Yes, please.
Okay. Yeah, so this is just by extension of that. Okay. So let's I don't my slide is showing. So let's then start. So what is this electrochemistry at all? Well, basically this is just the field of science or field of chemistry that unites electricity and then chemistry together. Basically, electricity has to do with flow of electrons. So how electrons are transferred from one point to the other, and the understanding of it from the chemistry point of view, it's this electrochemistry. So basically, we are just saying that in a chemical reaction, which is just driven by, say, an applied voltage or electrolysis that is created by chemical kinetics. This is just, chemical reaction. Sorry, chemical reaction. This is what you are talking about, electrochemistry. So basically, the branch which deals with this production of electricity, and that brings some chemical changes, what we want to refer to as electrochemistry. Well, we've much advanced in this the applications of this electrochemistry. Please, if you can't hear me, you draw my attention. It's raining, so maybe my voice may be down, but I don't know if you can hear me. If you can't hear me, you draw my attention.
We can hear you clear, but we are not seeing the screen.
Oh, please confirm for me.
Yeah,
please
see.
It's showing. Your screen is showing.
No.
Yeah, so it means that you are using a phone. So please restart the phone. Rejoin it again and see, because I'm seeing from my end that I've shared the screen is showing.
Okay.
So that's why I always want to confirm from others. So it means that it's either your internet or it's your phone. So you try to restart it. Is that okay? Okay. So let me try to. So basically that's it. So the field of study that deals with this transfer of that. Now we've as I mentioned, a lot of applications in there, but the most common ones are the batteries or these electrochemical reactions that leads to the productions of these electrons that we have. Okay, so we are far advancing in this electrochemistry aspect. So now we understand it more. So cars, instead of using fossil fuels, are now using these electrochemical reactions, which we call them the electric cars. I think in Ghana we wanted to sign up. I don't know how far that has gotten to, where we wanted to be using electric cars. Well, outside there, commercially, it's very common that they are switching from the fossil fuel to the electric cars. Most of them are switching to that electric cars. And this is just the application of electrochemistry. Okay, so I will start from the basis and then build upon that till we get to the much applications of that. Now, where does it start from? Well, the electrochemistry, the basic or the idea is that we're going to be releasing, transferring, or accepting electrons from a point. So then the idea of these redox reactions comes in, where a species is going to be losing these electrons. And of course, these are the electrons that are going to be flowing to generate electricity. And it happens in a reaction kind of form. So spontaneously, a species is going to be releasing, and then another species is going to be gaining these electrons. So I don't know if you remember your redox reactions. And those times, the basis was that we were just trying to balance. There's a redox reaction, and sometimes use that in stoichiometry. So do you still remember your redox reaction?
Yes, Doc.
Okay. So Basically, we are looking at it in this form. So if you have forgotten, I just do one or two examples, and then I proceed from there. So the reaction which we call redox, that is reduction oxidation reaction. So there is reduction, that is the reaction or the process where a species is going to be gaining electrons. Then there's the oxidation where there is a species which is going to be losing. So if you check a chemical reaction, you see that at the reactant side, when we move to the product side, there is a loss or gain of electrons, and it happens simultaneously. Not that there's a species losing the electron throughout, no species gaining. That is basically oxidation reaction. Then there's also a species which is gaining, that species that is just reduction. So, but then when the two comes together, then we're talking of having redox reaction. So this time when we want to just balance it, we have to just separate the equation into half reactions and balance the half reactions and bring them back to it. The overall reactions. Okay, I don't know if you remember, or you want me to go back to that and then build on that.
Yes, Doc.
Okay, let me get let me open a whiteboard and then get my mouse so that I can be writing. So I just do one or two examples, or just one example to refresh our mind, and also indicate that the interest here is just the electron which is going to be released or not. Just 1 minute. You can see my whiteboard.
Yes, Doc.
So let me try to give one example. Let's see. So, sorry, I'm connecting my mouse so I can write. Okay, so let me give you an example. For example, magnesium reaction with, say, iron. So let's see. So Mg reacts with Fe3 plus. Please, I hope you can see what I'm writing.
Yes.
Yes, Doc.
And this produces Mg 2 plus the Fe. Okay, so this is a typical example of a redox reaction, and that will separate the reactions into the various half reactions, and then we try to balance it. So if we try to separate that, there's the manganese solid or the magnesium solid goes to the magnesium 2 plus. And clearly you can see that the reactant was magnesium 0. It moves to magnesium 2 plus. So what is happening here? Is it oxidation or reduction?
Doc, it is
Oxidation.
it is oxidation. Yeah.
Has lost electrons, so that is oxidation. Then so that's one half reaction. Then we take the other one, Fe3 plus. So Fe3 plus moving to the Fe0. So the oxidation state for that ion is 0. So from +3 to the 0. So the more negative, the more reduced it becomes. So that is reduction. Okay. So again, sometimes chemistry speaks opposite of physics and then also the normal language. In chemistry, when we say you are gaining electrons, you are not becoming positive, but rather you are becoming negative in the sense that the electrons are negative. So if you are gaining, you're adding more electrons, then you're adding more negative. So you become more negative stuff. So this is reduction. Okay, so after separating that into the various halves, then we need to balance the individual species, and then we'll bring them back. So we balance the elements. After balancing the element, then we balance the electrons, and so we can get the equation balance. So if I take the first one, the oxidation reaction, the magnesium is 1, magnesium is 1, so that is already balanced. Now, if I come to the reactant side, the magnesium here is having oxidation state of 0. But the magnesium here is having oxidation state of +2. So how do I make both sides equal? Well, it's either, I subtract electrons from here, or I add electrons to this. So please, let me clean this one. Okay, let me rule a line here. So let me take the first one. So I'm dealing with this first one. So that's a magnesium, magnesium charge. Okay. So it means that to make this place 0, I need to just add electrons to it. Do you agree?
Yes, Doc.
Okay, so
Yes,
it means
Doc.
that this is balanced. So here I can see that that species is just losing 2 electrons. And if I take the ion, basically you see ion is 1, so that is balanced. Now the charge, this is +3, this is 0. So then how do I balance it? Means that if I should add 3 electrons here, so 3 electrons here plus Fe3 plus, Fe3 plus, I'm going to be moving to the Fe, and that means that this is going, so -3 plus 3, that is equal to 0. So that equation is balanced. So I need to just put them as in their original kind of equation. So I need to find the overall reaction. Now the overall reaction, if you look at the overall reaction, there was no electrons there. So I need to find a way of getting rid of the electrons. Is that okay? So it means that I just have to multiply this equation by 3, and then multiply this equation by 2. Please, is that okay?
Yes, Doc.
Okay, so that I can make the electrons here 6, and then the electrons here 6. And because this is at the reactant side, this is at the product side, when you move it, it becomes negative, or indirectly, it means that I'm crossing them out. So what it means is that now this one becomes 3 magnesium, and then 6. Now this one becomes 6 electrons plus 2 Fe plus 2 Fe0. So the overall becomes this electrons will cross this electron. So the overall becomes 3 magnesium plus 2 ion, 3 plus. Then it will move to 3 magnesium, 2 plus, plus the 2 Fe. Yes. Okay. Well, if I check, the magnesium is 3 at the reactant side, magnesium is 3 at the product side. Ion is 2 here, ion is also 2 here. Now the charges at the reactant side, it's 2 times 3, which is 6, plus 6. The charges at the product side is 3 times 2, which is also 6. These solid are just having 0 charge. So magnesium solid is 0, ion solid is also 0. So that's how we can know. So basically, you can see that at least 6 of these electrons were involved in that reaction. So this is how the whole thing starts from, or this is where it starts from. Trying to identify which ones are the oxidizing agents, which one are the reducing agents. Well, basically, if you look at it, there's fishy here, which is the magnesium. The magnesium is going through oxidation. But because it happens simultaneously, because magnesium is going to lose its electron, it's going to cause iron to gain those lost electrons. So in other words, then the magnesium is a reducing agent. It's the agent that causes reduction to happen. Please, is that okay?
Doc, please come again.
Okay, so I'm still using this equation which I've written there, magnesium and then iron. Now there are 2 species which are involved in this reaction. One is going to be losing electron, one is going to be gaining electron. Is that okay? Now the one going to be losing electron is going through oxidation. Do you agree?
Yes.
And the one that is going to be gaining the electrons is also going through reduction. Point established.
Reduction.
The one that is going through oxidation is going to lose the electron. But you see, it is the one that is, if not, that is going to lose these electrons. The ion will not have any electrons to gain. That is, the ion will not go through reduction. Okay, so then the magnesium becomes an agent of causing reduction. So we call it the reducing agent. So in other words, the reducing agent itself is going through oxidation, but it is causing another agent to or species to go through reduction or to decrease. Is that okay? Now, if you look at
Francis,
the other hand,
Francis, please mute your mic.
If you look at it on the other hand, the ion itself is going through reduction. But if not, the ion going to be accepting or taking the electrons from the manganese, then the manganese will not have gone through the oxidation. So in other words, the ion is causing oxidation to happen by just accepting that electron. And so the ion now becomes an oxidizing agent of causing oxidation. Is that point established?
Yes, Doc.
Okay, so that's how that's where we start from.
Yes,
so
Doc.
you'll be hearing oxidizing agent, reducing agent. That's just the interpretation of that. So at least if you have forgotten your balancing, I set one example. Maybe going forward, well, let me reduce this. We can try to, okay, so we can try to see how we can balance them and then also identify these. Yes.
Hello, Doc.
Yes, I'm listening.
Doc.
Yes, I can hear you.
So Doc, if you
I
see
can
the
hear you,
equation,
please.
and if you see the equation,
Yes.
and the one that is undergoing oxidation becomes a reducing agent,
It's a reducing.
and the one that is
Yes.
agent, the one that is a reducing agent, or the one that is undergoing reduction becomes
It's an oxidizing agent.
Is that right?
Yes.
Thank you, Doc.
Okay. So that is it. So please, if you have forgotten your basis, you want to go back to those bases and then we'll get to it. But the point here is that when redox reaction happens, there is a flow of electrons. And this is the electrons that is going to be creating or causing creating electricity, or we can measure the electricity and know the volts that is there. So that's the basis of it. So there's a flow of electrons, and here we want to understand how these electrons are being transferred from one point to the other. This is what electrochemistry is all about. And of course, we can look at the other side of it also. Is that okay? Now, I define some terms for you. So again, you've seen that I mentioned, oh, this 11 minutes the board. Okay. So I define those terms, reducing agent, oxidizing agent, and of course, I'm sure it's clear here. Again, we can hear terms like voltage, can hear terms like current, we can hear terms like charge. Okay, so that's, I also want to really define them so that at least going forward, when you hear some of these things, you clearly will know what is this thing. Number one is the current. I mean the voltage or that. Well, this is just basically coming from the electric potential difference between two. Sorry, a minute. Okay. Please, can you see my board? I've done it.
Yes,
can you hear me? Okay.
Yes, Doc.
Yes. Okay, so I'm trying to define that. So basically, voltage, we also call it the electric potential difference. And this has to do, well, difference means you want to find, so from one point to the other, so you want to find a change in there. So what's the electric potential in that? So basically, we want to measure the electric potential energy per how these electrons are going to be flowing opposite the charges that are going to be moving from one point to the other. So if we want to measure the electric potential of energy of a unit, I mean, if a charge is moving from one point to, and the point is just a current through a current circuit from one point to the other, then from one point, for example, it started from 3, then it's getting to say 5. We can find the differences between that, the potentials between that, then we measure that. So basically, the electrical potential or the electric potential energy, we measure that in volts, or what we call the voltage is measured in volts. So you see, we have V. So if you take, for example, a dry cell or what we call battery, you see that we can measure the potential, that's the charge flow from one point to the other, whether from the positive to the negative, how much of these energies are going to be flowing. So you see that sometimes we'll write, say, 3 volts. So that again, so in details, we're going to look at it. By potential, we can link it to, like, say, pressure. Okay, so potential just basically is just the push of these electrical charges, which I mentioned, from one point to another through, say, a wire. So it's going to, the charges are going to go through a wire in a circuit from one point to the other. And the energy that is involved is what we are calling the potential energy, the electric potential energy, and we measure that as in volts. Well, we have a simple formula which we use to calculate that, and that volt basically has to do with the energy divided by the charge. Again, we'll come to the details, but just to, as a form of defining these terms. So volts or voltage basically is just energy, and of course the energy can be work done because they all have the same unit. So work done, or the energy which is involved from moving from one point to the other, and the charge which is moving that too. So energy, the unit for energy is joules. The charge, the unit for charge is coulombs. So we have this unit. So that will become, so the voltage which we measure is actually joules per coulomb. Okay. Well, if you look at the voltage that we can have the alternating current voltage, that is like your home socket. And then we have the direct voltage or the direct current, which is the DC, like the batteries that we use. But in all, you will see that they've measured the type of volts that we have. So, for example, our appliances will have some volts, which is being defined there. So, you on your phone charger, I should check mine. So, for example, I'm having my laptop battery here says that I should be having a voltage of 5 volts DC. So if I'm going to be plugging in, then I should know the flow of charge that goes in there. So that is the voltage. Now let's move on to the charge. So the electric charge is what causes the electrons to have, of course, move. Once the electron moves from a species, it creates a charge. And of course, the electrons moves in the opposite direction as the charge. So in electric current, that is just how we causes that flow of electrons to move from one point to the other. And so we also measure the unit for charge, as I mentioned, is just the coulombs. So we use coulombs as a unit for measuring electric charge. Now we have what we call current. So this is going to be flowing from one point to the other. Now that energy which is flowing is the voltage. By the time it takes to flow from that point to the other is what we are calling current. So I don't know this time, but those times we see that we say that the current is half current. I don't know if you have heard that before. So you see those times that we're using this yellow box and those listen, now I don't often hear of this half current and those things. But then those times is used to. So what it means is that the energy which is flowing from the point, and the point can be either coming from the generator or coming from the source like a ECG to our point, which is where the bulb is, the flow of that particular time. So the energy which is coming, for example, if it is say 5 volts, it is assumed that the 5 volts should come in every second. So well, later we'll be doing the time jumps and those spectrum. So we'll get to it. So if, for example, every seconds you need to be getting 5 volts. Now the 5 volts comes in say 3 seconds. There's a delay in time. Once there's a delay in time, the current will be affected. Please, is it making sense?
Yes, sir.
Okay, so that is how we define the current. Okay, so I guess these terms are common to us, and so we'll get to have much of that. So basically, we measure current in amps or the ampere. That's a unit or symbol A. So electric current, or what we call current, is just the electric charge which goes through a conductor.
Hello. Is dog network on? Hello.
I guess so.
Okay. Yeah. Hello. This went for a network. It will kill us.
Hello?
Yeah, hello. I don't
Yeah,
know.
dog.
The
Hello,
internet
dog.
is
Hello, dog.
the internet is not stable for me at all. I don't know why. But you let's try to manage it. Let me off my let's try to manage it. I think with time it will be corrected. Okay. So let me share my screen. It went off. Yes, so please you get what I'm trying to say. Yes. Am I off again? Hello.
Yes,
Yes,
Doc.
we can hear
Dog, we
you.
are on.
Okay. Yeah, so I tried to explain the current and then voltage and then charges. But then, of course, there is a relationship between current and then voltage. And that relationship was possible from Ohm's. So Ohm's law gives us this relationship. But then Ohm's law says that current will be more or less like related to voltage by how these charges are going to be flowing and how they are going to be resisted. So current basically is just a voltage over resistance. So that's a relationship. I don't know if I did it right here, but so let me go back to so the relationship between current, which is I, and then voltage is voltage over R, and then R is basically resistance. I started with the please remind me which one did I so that so voltage, right? So I defined voltage to be work done divided by the charge. Okay, so work done or energy divided by charge. And then, of course, we can then relate. And current is equal to, or let me use I for current. So current is basically the charge or the electric charge moving at a particular time. So that is, so I Q, I is equal to Q over T. But then voltage and current is related together, and that's it's related by this resistance, the inverse multiplication of resistance. So that's so this is what we call the Ohm's law. The Ohm's law. Please, is that okay? Hello, please.
Yes, Doc.
Yes, Doc.
Yeah. Okay, so then we can move on. So you see that the phone charger will write the say 5V, that is 5 volts, or it might deliver 2A, that is it might deliver out of that flow, it might deliver 2 amps. So we just have to know that that's once we say the amps, then we are talking about the charge which is moving at a particular time. The time here it's reported in seconds. So of course, when we are doing the calculation, we try to convert that into the ISI unit. So that we should note as part of the technology step. Now, again, in electrochemistry, you'll be hearing other terms like, of course, I've mentioned oxidation reaction, reduction reaction, but then you hear like cathode and then anode. Okay. Now, if you look at it, we can basically split based on its application into two aspects. We have using electrical, a chemical reaction to generate electricity. That is one. Then, and that is what we call the electrochemical reactions or electrochemical kind of cell. So we are using this chemical reactions to generate electricity. That's a redox. So you see, it's just a chemical reaction, but the chemical reaction is producing electrons. And of course, flow of electrons is electricity. That's one. Then two, we can use electricity to spark chemical reactions. Please, is that okay? So there's a flow of electrons, and that flow of electrons will now initiate a chemical reaction. So basically, if you are looking at it in terms of application, you see, we'll be talking of these electrochemical cells, and then which is the galvanic or the voltaic cell. Then we have, sorry, somebody talking.
No, Doc, I'm only trying to write this down. We can use electricity to spark a chemical reaction. Please, am I right?
Yes.
Thank you.
And that's what we call the voltaic cell.
Okay.
Okay, so these are terms. After the terms, then we'll then deal with the. So I'm just introducing you to some terms, and of course, as in the Chem 203, I think some of these terms came up, but then as form of a revision, so that you get to have these terms, and that's why I'm revising. So if you take the electrochemical kind of reactions, you see that we're going to have, of course, a chemical reaction producing electrons, like we saw with the redox, meaning there's going to be reduction, and at the same time, there's going to be oxidation, so that there'll be flow of electrons from one point to the other. But a typical example is our phone. When we are charging our phone, redox is going on there. Okay, so there's these applications that are absorbing your electrons. Otherwise, then there's no need to charge your phone. Once it's full, it's full. But then the applications there are now becoming or acting as reduction or going through the process of reduction. Then you put into, once they use the electron, you have to bring another electrons, that kind of system. Okay, so we'll be hearing at that point where we are having reduction, that there's a species which is going to be going through that reduction. And of course, in some electronics, the conductors that we have there, you see that they give out electrons. And that's one point also accepts that electron. So there's going to be a flow of electrons in the system. And opposite that electrons, there's going to be ions also flowing. So if you take a cell, for example, and oh, sorry, I'm talking, but the whiteboard is still on. Okay, so if you take a cell, well, a cell basically we can that's as I mentioned, it can be the electrochemical cell. So, for example, we have a solution which is of course a compound in water, and then we have some rods which these rods are called the electrode. So the electrodes are the ones that are going to be receiving the electrons, or they are going to be receiving the charge. So the rods that are there. So at a point you see that, so just as I'm showing, we have this copper rod or the copper strips, which are, of course, copper is metal, so it can allow flow of electrons, that is, it releases or then gain. And we put this copper into a solution of copper sulfate. So the ions, once it's going to be in that solution, that's in the aqueous. So basically, we're going to have the cations and then the anions in that form. Once there's a cation, basically what we need to understand is that it has lost an electron, and the electron is moving opposite where that cation is supposed to go. Is that okay? Okay, so once we have a cell,
Okay,
we can also know where the electrons are going and where the ions are going. So please note that. So the chemistry that takes us, or that's help us to understand where the reduction is happening. Of course, the reduction is happening, for example, in the electrochemical series. We'll see that the cathode is the point or the electrode where the reduction is happening, and then the anode is where the oxidation is going to be happening. And these are, if I say electrode, these are, I mean, element in their elemental or in their ionic form. So, for example, copper becomes the electrode which is going to be gaining the electrons. So that's reduction happening at that side. Maybe at the other side, you see zinc also becoming or releasing the electrons. So that is where the oxidation is happening. So I don't know if I am, let me try to just write here. So a ball pen. So let me write on top here. Okay. So copper, no, it's not going to write. Please a minute, ball pen plus red pen. Okay, so copper 2 plus, I hope you can see it. Copper 2 plus,
Yes,
plus zinc. Okay, then producing the zinc 2 plus, producing zinc 2 plus, and then copper 2 plus, so plus, so plus copper. Okay, now these are the two electrodes, the copper and then the zinc. Okay, now when you look at it, you see copper 2 plus to copper 0. What is happening?
the copper is
Oxidation.
oxidation.
Please,
The copper is
it's
gaining.
not, when you are gaining something, it's not oxidation.
It's
That's the reduction.
It's reduction.
Reduction.
The copper is
Please, I
gaining.
just
copper
mentioned
is
that
reduction.
in chemistry, when you are gaining electrons, you don't become more positive, rather you become more negative, and that is reduction. So the copper is the electrode where the reduction happens, and so that is where the cathode is going to be.
Negative.
And
Okay.
then the zinc,
Plus 2
the zinc is where so if you look at zinc 0 to zinc plus 2, that is oxidation. So that is the anode. So the copper becomes the cathode, then the zinc becomes the anode.
reduction.
Yeah, so the zinc becomes the anode. By application, we use this cathodic reduction, for example, in terms of, say, jewelries, we use that to coat. So we come to corrosions, we use that to protect those metals so that at least it's the first coat which is going to be going through the reduction, other than the main kind of jewel that we want. So if we want to protect, say, silver, we coat it with copper, so that it is a copper which is rather going to be gaining the electrons from its environment, not the silver. So that will protect our silver and always makes it look nice. Like this stainless steel which we have, like the steel. So we use that cathodic reduction to protect that as well. But then what I want to mention here is that cathode will be happening at the, reduction happens at the cathode side, whilst oxidation happens at the reduction side. So please note that.
And
Is that
Doc,
okay?
please come again.
Doc, please come again. Doc,
Okay.
it didn't end up that cathode at the reduction side
So reduction,
anode at oxidation, right?
yes, reduction happens at the cathode for electrochemical cell. The other voltaic one, it is going to be opposite. So please note that. That's why I said note that. So for electrochemical cells, the reduction is happening at the cathode, and then the oxidation is happening at the anode.
Thank you, Doc.
So if I say anode, definitely you should know that that is where oxidation is happening. So we come to the cell, and so you know in that cell, when, for example, I write this copper 2 plus zinc 0 moving to, this is a cell. So when I say that the copper is the anode, then you should know that the anode is where oxidation is happening. So you know that that is where the electrons are going to be flowing from. You know, we are saying that it is starting from a point to another point. So it is starting from the oxidation to where the reduction is happening. Is that clear? Okay, I think so. We just take note of that as we try to move on. And this happens in the redox a lot. So you know that electrons. Yes.
Look, why is it vice versa in vortex cell?
You know, as I mentioned, in the electrochemical cells, we are using a chemical reaction to generate electricity. And then in the voltaic, we are using electricity to spark a chemical reaction. So it's a reverse kind of something.
Okay. Many a time our learners ask us.
Yeah, so it's a reverse basis. So once this one, the oxidation is happening at the cathode. When you reverse it, the reduction will now be happening at the cathode.
Okay. Thank you.
Okay. So don't confuse yourself. I gave you the two extremes, and now I'm dealing with one. Then later I'll come to the other one and also deal with that. So I'm looking at the electrochemical cell.
Doc.
Yes, please.
Doc, if you can repeat that one for me. At the electrochemical cell, you are using the chemical cell to generate electricity, but at the vortex cell, we use what to generate electricity?
We use electricity to spark a chemical reaction.
Okay.
Are you okay?
Yes.
Yeah. So, for example, what is this? Let me think about an example of that. But okay, let's move on. The example will come. I think I have that in my slide. So let's take the complete cell. So when we take a cell, what are the components that we get to see in that cell? Number one, you see the electrode which I just mentioned, where the oxidation is going to be happening, where the reduction is going to be happening. These are the rod there. So we can say that we have the anode electrode, then the cathode electrode. Is that okay? Now, these electrodes are going to be connected by wire, and of course, we can measure the voltage, which is going to be flowing throughout a point. We can also look at how we can measure, once we know the voltage and we know the resistance, we can measure the current. So it's connected by wire. Of course, these electrodes are in a solution. We place them in a solution where the electrons flow will lead to charges, electric charges also flowing in the opposite direction. And so we need to connect the two solutions together where the charges are going to be kind of flowing also. Now, these two is done by what you call the salt bridge. For the salt bridge, we can use the glass tube or a paper where the solution is just exchanging ions in that. So this is a component of a cell. Okay. Now, this is a general overview of how this is going to work. So if I take the first part, which is the electrochemical cell. So here we are going to be seeing that electrons are going to be produced by the anode. So if I say anode, what do I mean? And why am I saying electrons are going to be produced by anode? What is happening at the anode?
That is where oxidation is taking place.
Yes.
So that is where the oxidation is taking place. So the release of electrons start from the anode, that is the oxidation, then it will be carried to the cathode where reduction will be happening. Okay, so you just have to know that. So it produces from the anode and must be consumed by the in the cathodic reactions. You get to have the reaction, the electrons get into being reduced. And so you see that there's always the pair that one must lose, one must gain. If one is losing and there's nothing to, or there's no kind of electron to gain, that is not a redox, and of course the flow of electrons at a point is going to be ceasing, and that's like a oxidation reaction. It's not a redox reaction where the flow must just go down. So these two electrodes must be combined, and we combine them or we connect them with wires, and then we connect them by measuring their voltage, or say we use that to on our bulb. And of course we know that there is a flow which can produce this power so that the bulb can be on. So in the electrochemical cells, we will see that we are just having these electrodes being placed in a solution. And of course, the electrode there are the ones going to be releasing the energy. Of course, the solution is what we call the electrolytes. Okay, so we place the electrode in electrolyte. And this is what is going to be generating the electric current in that sense. So on the other hand, you see that we'll say that the electrochemical cells are going to be used externally to supply electric current, which is being driven by a chemical reaction. And this reaction must happen simultaneously. If it is not simultaneous, that is not redox, and so that will not be having the electrons flowing. If I say flowing, not just moving and stopping, but then it should continue. So for example, as we are speaking, your phone is on, your laptop is on. Now, if it is not redox going on, flowing, then at a point when you release a 5 volts, that is all. Just so it will just come like a flash, then that is all. But then it is continuing flowing, meaning there is this spontaneous or just simultaneous reactions going on in there. Well, the electrochemical cell, we normally call it the electrolytic cell, or in other words, a galvanic cell. Okay, so that's that. So we will see that a chain that we have the galvanic or the electrolytic cell, and then we can have the voltaic cell as well. Okay, now the first kind of cell that we first developed was from Daniels. So that's the Daniel cell, which I'm showing here. And that Daniel cell has to do with the copper zinc example that I gave earlier. Okay, so if I want to show how it looks like, so this is a picture which I took from a book, and let's look at its representation and of form. So we have, let me see. Please, can you see my pointer? I'm moving my red pointer. Okay.
Yes,
so
yes, we can see.
Okay, so if you look at it, you see that, for example, the zinc here is going through, is going to lose electrons. Okay. So from 0 to +2, it has lost electrons. So that is oxidation happening there. So in that case, what is the name given to that electrode? I just want to test if you still following that. So when oxidation happens, it happens where?
At the anode.
At the anode.
Okay, that's okay. And then the reduction will be happening at that. So it means that for Daniel cell, the anode is where the zinc is, and of course, that is on the right, and then the cathode is on the left. Okay, so you should know that the electrons are moving from the anode to the cathode, but then the charges will then move from the so opposite of that. So if the electrons are moving from the anode to the cathode, the charge will move from the cathode to the anode. Okay, so in electric Daniel, you see that the cathode side will give it a positive sign, and then the anode will give it a negative, meaning the charges will be moving from the cathode to the anode. Okay, so that's the Daniel cell. Of course, it was used in, you can measure the volts, we can use that to on that. Now you see that the electrolyte is being connected together, and how we connect the electrolyte is the use of the salt bridge. And as I mentioned, 2 examples of that. Whether we can use paper, which is just like using capillary, so that it moves up and down, so ions can just be easily moved. Or we can use a glass tube, so with the holes there, like bend like a U shape, so that this electrolyte can move from one point to the other, and by moving, it kind of moves the charges also from that. So we should get to know that. So that's the Daniel. So you see that in such a reaction, the sulfate ion plays an important role. So in the electrolyte of that Daniel cell, behind the sulfate kind of solution. So zinc sulfate, copper sulfate. So the anion there is a sulfate ion, which is carrying the charges from that to that side. So we'll say that the sulfate is going to play an important role, and the sulfate is a negative charge. So the anion there, which is SO42 minus, is going to play an important role where these anions built around the anode, and that will make, because once there's this positive thing, charges, once they are losing electrons, it's going to be more positive. So this anion gather around the cation part, which is the anode, so that at least it can balance it and make it neutral. And of course, at the cathode, you're going to see that you're going to be having these copper ions also being produced, and that is also going to be balanced with these anions as well, so that the system becomes kind of a neutral charge. So these 2 processes is what really balances our flow of electrons.
Hello, Doug. Hello, Doug. Hello, Doug. Hello, Doug. I can't see your screen. No.
He's saying he's off. Oh, the screen is off.
Network idiot. No easy. Donc, move faso. Ça. We said that you too.
I'm not trying Daniel Son is saying in a man movie, no screening soon memory. That's what Casasa.
Daniel Son, now he was representing the electrochemical cell as an example of electrochemical cell.
But no, we should play a diagram of the children.
I diagram.
Well, Miss Queen never be my dad.
Doc about buying a scam.
That needs not to say.
This internet is going to. Please, can you hear me?
Yes, dog.
Yes, dog.
Yes, we can hear you, but the screen is not showing.
The screen is now loading. It has loaded. So
Yes,
I think somebody was talking, or it was a question. Okay.
No, it was about this in the screen.
The screen, you see, as I mentioned, it may be internet from your end, or if you are using phone, it does happen.
I'm using laptop.
And so then it may be internet or something. That's why I always say that the others will confirm. So if it is like from my end, the others will also not see it. But if others are seeing, then it means that it's from your end. So are you seeing it now?
No.
Please confirm.
But it's on.
So it means that yes. So the best will be that you restart your browser and see if you can come back. Yes. Please let me hear you.
I'll be glad if you start from the Daniel. My network went off.
Your network went off.
Yes, dog.
Okay, you're taking me back. My introduction will take long. I have not yet started the main course crowd. Okay, let's go back. Where's my slide? Okay, so we want us to look at the first the chemical cell. Please, is this one right?
Yes, dog.
Hello, dog.
Yes.
Hello, dog.
Yes.
Please, I'm Maxwell.
You are what?
Maxwell.
Okay. Yes.
Please, dog. Please, somebody is saying that his network went off. Please, that one we can't accept it. And dog, I suggest we should go ahead.
Okay.
But, dog,
I'll quickly run through. Then
Maxwell. And dog, Maxwell. On your yes, dog.
Please, yes, let's one minute.
Yes. Dog, please take time and hear me. Please, what I'll plead on your lectures is that let us know the basis and what we should expect in the exams. So that as we learn, we know that, Doc said these things should be coming in the exams. Because that is the only thing that is lacking. Because we learn and write exams and we have to pass. But you lecturing us on all the aspects, and we are not getting the concept based on our exam. So before we realize, so please, we beg you, give us the guidelines for the exams.
Are you done?
Allow.
Are you done?
No, allow Doc to letter.
Please.
Not,
you see,
we are not learning for exam. No.
Please let me talk. If for exams is the reason for exams that you join the course, that I'm sorry, I'll disappoint you. I'm very sorry. I don't teach for exams. So I don't know if you have seen some of my questions. If it is for exams, that is why you are here, then you fail the course. That one I can promise you. But then you are here to understand and apply it as a teacher or as an expert in that business. So please get the understanding, the overview understanding of the course and apply it later, not just for passing exams. I can give you tutorials, I can give you questions and answers, and eventually you still fail because you did not understand the thing. Because once I give you tutorial questions, I can bring the same question, but then modify it in a practical way. And because you did not understand the concept, you cannot apply it. You see the question all right, but you cannot apply. So if it is for exams while you are here, I am sorry I can't go that tangent. Now again, you should note that all the students have paid for a particular package. And this is what I tell students. Please allow other students to benefit for what they have paid for. Nobody is here to understand more than the other. So if somebody says that I'm not clear about this point, the person must be clear because he paid for that. And that must be addressed. You don't go buying for an iPhone and then they give you a young phone and it says, okay, once I can use it to make call, I'm okay to go. That is wrong. Is that okay? So once you pay for iPhone, get your iPhone before you go. That is the reason why you are here. So we are not here to pass exams. If you are here to pass exams, then I'm sorry you'll be disappointed. And that if somebody doesn't also understand something, feel free to ask and let us. Maybe it's just communicating. It's just communication. I'm not communicating well. And so Albert Einstein says that science should be explained so simple that a child must understand that science. So if I'm communicating and you don't get it, you draw my attention, I can change the language for you to just get it, and then we'll move on. And that's why I'm moving that flow. Well, at a point in time, if the course content, which so after this class, I'm going to share the course outline. We're going to see how the course outline is going to be, or the topics which are going to be in that. And of course, I'm going to attach some tutorial set also there. You're going to see how questions and answers are being done. And then I'm going to attach the notes or the slide also, which you can read on your own. My responsibility here is to explain the concept. That is all. And I must say that the instruction given from code is that this is switch. Is that correct?
Yes, Doc. Yes, please.
This is not regular code. So the advice is that we should treat you people as our regular student, not the regular code. If for regular code, there's a book for you, which you have to just read chapter 1, chapter 2, whatever, and then there's a facilitator who comes to talk, the rest you go and read. But you are not regular code. You are a student, which is just like you coming to a regular chemistry class or regular education where you are sitting in the chemistry class. So please understand that. So we need to give you much details like we are going to be giving to the regular students. Now I think that is addressed. So let's move on.
Thank you, Doc.
If you have an issue you want to bring it up,
Doc,
that's okay.
It's me.
I saw a hand. Okay. Yeah, I saw a hand. Is it addressed? Okay.
Doc,
So
Doc, I said,
no,
Doc, I said you should start from Daniel Cell.
so I'm going to go back and then move that. But then I should send this caveat. If I look at the pace which I'm going, that's why I decided to create this 2 hours. I mean, two separate days so that we can move and then take much time in that. And that if it's not going to help, then at a point we need to rather drop or, if possible, increase that, because it's just what was the credit hours? Is it 3 hours or 2 hours?
It's 3 hours.
Yeah, 3 hours, and I added another. So basically, if the time is not enough, then I'll advise that we create much time. It's not that I like teaching, but then at least we need to finish the content in a particular space of time. And that is why I created that extra time. So for me, if you look at it, 3 hours, and you are meeting how many weeks? Ideally on the timetable, how many weeks are you supposed to meet?
4 weeks. 4
weeks. Now, if I create, say, 6 hours, and that's 3 times 4 is just 12 hours. And that is what Cody will be paying me for that, just 12 hours. But I feel like I should not, there's no need rushing through once the people don't get it. So I create extra time, and then they will just pay me 12 hours. That is all. But then I don't mind going more than 24 hours just because I want the content to be captured, and they pay me my 12 hours. That's okay. So please, let's tolerate each other, and then let us understand what is going on. And then once you understand, you are ready to answer questions. I don't want the situation where at the end of the exams, at the end of the quiz, students will be sending me messages that consider. I don't, meaning you were ready to write exam. The exam came through, you didn't do anything. Now you are telling me to consider. So please, let's tolerate each other. And then, okay, the Daniel cell, and then I will just move on. So can I go on?
Yes, Doc.
Yes,
Doc.
So this is the first cell of this. Daniel cell is a typical example of this electrochemical cell, which was the first one, which was developed by Frederick Daniel in around 1830s thereabout. Okay, but then if you look at the diagram, the cell diagram which I'm showing here, you will see that the Daniel cell consists of 2 half reactors. It consists of the anode and then the cathode. That is, it is where the oxidation is happening. That is the anode side, and the cathode is where the reduction is happening. And the anode is the zinc metal, and then the cathode is the copper metal. These are the electrode which is involved. Now we put this electrode, I don't know, can you see my pointer?
Yes, please.
Okay, so we put this, so we have the anode that is on my right, and then the cathode on my left. Now the anode is where the electrons are going to be flowing. So look at it, as I mentioned, electrons are going to be flowing from the anode to the cathode. Is that okay? And then the charges are going to be flowing opposite that. Okay, now the charges goes along with the ions in that, and so you see that these electrode, which is the zinc metal in the anode and then the copper metal in the cathode, are placed in electrolyte. That is a solution. Now the solution is the zinc sulfate and then the copper sulfate. Normally the anions should be the same, so that when there's a flow, that will not contaminate the cell. So the anion is going to be flowing from one electrolyte to another electrolyte, which is through the salt stream. Is that okay? So in this Daniel cell, the salt bridge is what, so you see the 2 arrows there, you see that the ions are moving in and out of that. And the ions here is a sulfate ion. And I was saying that the ion plays an important role because when the anode part is releasing the electron, it becomes positively charged. And we need a negatively charged to balance it, to make it neutral. Otherwise, the system will become positive, and then finally it will not get any electrons again, because we can release all the electrons. And again, when we don't balance the cathode side, it will also be accepting the electrons. And so basically the anion here is like a carrier. It carries electrons to the anode, and the anode will release the electron to the cathode. Then it will carry an electron from the cathode so that the cycle will just continue that. In that case, what it means is that it's just trying to neutralize the system so that we don't get to have some part becoming negative, some part we go. So Daniel cell basically, it has these two parts. So electrochemical cells has the two parts, the anode part and then the cathode part. And of course, the anode part is the zinc. In the Daniel cell, the anode is the zinc metal. Then the cathode is a copper metal. And they are all in solution, sulfate solution. So copper sulfate, zinc sulfate in that electrolyte. So that's the information we are getting from the Daniel cell. So I try to use these the ion there to just define or just try to explain this neutralization of the solution there. Please, are you okay?
Yes, Doc.
Okay. Now let's look at the other side of the electrochemistry, what I was just mentioned. So Daniel cell is an example of the galvanic cell. Then we have the electrolytic cell, which is the voltaic cell. And that has to do with we're trying to use electricity to spark a chemical reaction. So that is electrolysis. So releasing of electrons, and these electrons will be then getting or releasing. Once the electrons are being released, then there's a chemical reactions which will be started with. And that is the electrolytic kind of cell. Okay, so if I want to release, make a summary of that, you're going to see that it's just a reverse of please, I'm not seeing the online this thing. So if you send a message or something, I can't read it, but I'll prefer you just unmute and then you talk. But then
all right, Doc.
I have to.
I actually raised my hand.
Okay, I have
Doc,
to.
by convention, I know for the voltaic cell, the anode is supposed to be on our right. Sorry, the anode on the left, and then the cathode on the right. But what I see in your diagram, you have the anode rather on the right and then cathode on the left. So I just want to know whether it can be interchanged.
Wait, don't confuse yourself. We said voltaic cell and then galvanic cell. They are not the same. Okay, I just mentioned that. Okay, you will be clearing those doubts as we get into much distance. So you see that where they say Daniel cell, we'll be clearing. I'm going to be giving much examples. So you hold on. Let's address this as we move on, right? Okay, so let me make a summary of this chart. So if you take, of course, a general electrochemistry or the electrochemical cells, we will have to deal with the galvanic and then the electrolytic cell. Well, the galvanic cell, which much at times we normally have much application, you see the primary cell. Well, when cells are put together, we call it battery. So again, you see me showing the battery here, but then these are cells put together. That's what we call the cell. So we have the primary cell, which is the one that are just going to be producing the voltage just like that. After the electrons are fully used, you can't do anything with that again. You just need to dispose them off. But again, we have the secondary cells where once the electrons are fully used, you can push in another electron. So the secondary battery is where we can We call it a rechargeable battery. Sorry, somebody talking. Okay, so the rechargeable batteries are called the secondary cell. So, for example, the car batteries, they even are phone batteries. These are secondary batteries. Now, currently, the phone batteries that we are using is actually having a lifespan. Unlike the previous phone battery where you can remove the charger, the battery, I remember those times you can even have this universal charger to charge it. So you can basically remove the battery from it. So once the its lifestyle is expired, you just need to replace it with another battery. But these new phones have closed, like for example, new laptops. We don't, first you can remove your battery and then replace it, but now is in kind of embedded. Once the lifespan is kind of expired, you just need to throw the whole laptop away or throw the phone away. The highest you can charge is not going to cross 50%. It is going to run down within a few minutes, meaning it has expired, it cannot hold much electrons again. And of course, manufacture and then the idea. Okay, so at least if they give you a phone which will be lasting for 20 years, then their company will have to close down. So they give you a phone, and the lifespan for the phone is 5 years. And that's why I advise that when you are buying, especially electronics, don't buy the used electronics. For example, phone, laptop. It's better you add on and buy new one, because the person have used it for 5 years, it started creating problems, and he gives it to you at a reduced price. You also will not get it as a new. You can upgrade it too, but then once a lifespan has expired, that is all. And that's how the secondary batteries are used. Now we have the fuel cell, like the hydrogen cell, which now cars are now going, because once, they talk of this global kind of warming stuff, but of course some part of the world, they are really into trying to make sure pollution is being reduced. So fossil fuel really releases a lot of these methane, a lot of these CFCs, which is creating the ozone depletion. And so they want to resort in these electric cars, or basically hydrogen cars, or these hydro cars. And these are purely like, once I have the cell, the fuel cell, all that I need is to put water there. Just like we are using water to generate light. Okay, so like a Kosomo. So once you push in water, the water generates electrons, the car is moving. So you don't need to buy fuel, you are just putting it. And this is how the hydrogen fuel also works. Just isolate or push as it moves on. So let me take the first part. I'm taking this part, the galvanic cell, and then we'll look at it into detail.
Hello.
Then I come to the electric.
Mr. Sergio, can you please mute your mic?
Okay. I don't know. I can't mute it, and I have to be going up and back and forth. Okay, so please, if you are not asking, if after questions you have to mute yourself. I think all is muted. Let me go back. Okay, so let's take the galvanic cell. Well, named after Gigi. Yes, Galvani. Yes, please.
Hello,
go ahead.
Now, please, the secondary cell, can it also be called the wet cell?
We have, under the secondary cell, we have dry cell, we have wet cell. So we can't just give one example or one type of secondary cell as secondary cell. We have the dry cell, we have the wet cell. I'm going to be showing it very soon.
Okay.
Is that okay? Okay. Yeah. So I'll be talking. So as I said, I'm following this flow chart. Okay. So I'm taking the galvanic cell. Then later, sorry, where is it? Okay. So I'm taking the galvanic. Later, I'll take the electrolytic cell. But under the galvanic is this type of cells that we just want to. So as I mentioned, the electrochemistry is covering the zinc and then the copper. Please, when you get that, please note that. Or let me do the correction now. So I'll skip. I'm going to go down so that I'll push this one. Now, I mean it. Let me do this so that when I'm sending it, you. Oh, that. Okay, so please, a minute. Let me do this. Okay. Yes. So this is it. So for every galvanic cell, we have the two parts of this galvanic cell. We have the anode, then we have the cathode. Now the anode here, just like the Daniel cell, is the zinc, and then the cathode, the electrode there is the copper, and they are all in the electrolyte connected by the salt bridge, which is going to be transferring or transporting the anion, which is the sulfate here. Okay, so the voltaic or the galvanic cell. So this is what we have. So again, note that the anode is at my right, the cathode is at my left, and the electrons are going to be flowing from my right to my left. So that's we should just know. Now, what happens or what goes on in the galvanic cell? This is a question which we need to really address. Now, what goes on there? And what is going on here is that we are having, sorry, oh, we are having the zinc metal or the zinc electrode, which is going to be releasing electrons that is going to be oxidized, and this oxidation really pushes this electron to the copper side so that the copper will be gaining that electron, and that the anions, which is the sulfate, comes to neutralize the copper, the zinc, which is being positive here, so that the whole system will still be operating in the neutral medium. Now, the second part is that the copper will be gaining the electrons. And again, once the copper will be gaining the electrons, of course, the concentration of that solution will be reducing. And so the anion again must flow back to really reduce that kind of form. I see in the galvanic cell, the whole thing happens simultaneously or spontaneous kind of a chemical reaction. We said not that we are saying it just like it's separate, but then it happens just like that. You don't separate the two. Once this one goes, this one comes, and then it's just so that the flow can really continue from that. Now, you can see from the galvanic, we have the cell diagram. We have, of course, the figure for that. So either we draw it this way, where we have this cylindrical stuff, where we have the electrode inserted it with the salt bridge connected to the voltage, or we use what we call cell diagram to represent that, and this is the chemistry of that. So either we draw it or we use a notation to represent the whole thing. Now, the cell diagram basically is just a shorthand for writing the chemical component of this electrochemical. So it's either, the drawing whole thing, we are not doing art, but we should have a very simple.
Network.
Please, Doc, your screen is off.
Hello, please, can you hear me?
Yes, Doc.
Doc, you want first?
Yes, please.
Yes. So when we are drawing the diagram, these are the steps, or these are the conventions which we should note. And that goes to address, so your concern about that. So I think we're right. Somebody raising hand or he left. Okay, please, let me focus on my slide. Yeah, so in the cell diagram, what we need to know is that we normally place this anode on your left. That is if you are facing the book. And then your cathode at your right. Then we draw a single line, which is just going to be the face. We use that vertical line as the electrode, which is just going to be connected with some kind of scale, which we normally say that is a wire. Then yes.
No, please, your slide is not showing.
Please
Yes,
confirm.
please. Yes, it's not showing on my side too.
Please confirm.
Yeah, Doc is not showing.
It's not showing.
Please, it's showing. Maybe it's the person's network. Try and adjust yourself to one or the other.
I just said it. I think it should show now.
It is showing.
Okay. So please, that's how I confirm. So normally try to ask if others are off or yes. So where's my slide? Yes. So that is what we use in kind of this cell diagram. But of course, instead of drawing that art kind of this, and we chemists, we normally, just like when we're dealing with this periodic table stuff, I don't know if you've done main group or so stuff. So you see that instead of, say, writing hydrogen, HYDROG, a chemist doesn't want to be wasting time. So it says H. So we have a chemical symbol for the element. The same way, instead of going to be drawing this diagram with those things, we have what we call the cell notation. So we devise a shorthand in representing a cell just using a notation. And that is what we just represent. So in that case, we'll just be noticing the two half equations. And then that half equations will represent our anode and then our cathode. So we have, for example, a cell. This is a cell showing there. Please, you can see my cursor. Let me change it to red. Okay, so this is a cell showing here. Okay. Okay. Or let me use this one, so that this a platinum hydrogen cell. But let me use this one so that the explanation comes out clear. So I'm using the magnesium aluminum cell. Now this is a cell. Now you're going to see that we write a half equation. So this is the oxidation following by the reduction. So we write the anode, followed it by the cathode. Is that okay?
Yes, Doc.
Now, if we write the anode, when we are writing the half equation, it's supposed to be magnesium, then there's an arrow going to magnesium 2+. Now, in the cell notation, that arrow is represented by just one stroke. So you see magnesium stroke magnesium 2+. That is one half equation. So that's the reduction will be aluminum 3+ 2 aluminum. That is one half equation. Then we use a double stroke to represent the salt bridge. Okay, so if I should say I want to draw this. If I want to draw it, I'll draw it this way. Two electrolyte. Then I have my electrode here, another electrode here. Then I'm going to connect this electrode with my a wire, and then I'm going to connect these two with my salt bridge. And this is my the cathode against my anode. But when I'm writing, so if I'm writing the half equation, I write the anode. So the anode equation, I write the anode followed by the cathode. Okay, and then I separate the two with the salt bridge. So this is the salt bridge, the two strokes. And then one stroke is just the arrow, which I'm just going to be using to differentiate. So please note that the spectator ions, which will be the ions that will be left out when we are writing. So there's, for example, if you are using the Daniel, the sulfate will be left out. We don't include that. Now the salt bridge, we use double stroke to represent salt bridge. Then the arrow, one arrow is just one stroke to represent that arrow which we write. Please, I'm sure this will be clear.
No, can you repeat? The spectator ion which is left out is there. If you are using the Daniel cell, it was
the sulfate. The spectator ions, which is the sulfate, because it does not form part. It's only carrying or is being carried so that it will bring neutralization, but it's not part of the releasing of the electron. It doesn't release electron, it doesn't accept electron. That's why we are saying it's spectator ion. So we leave that out.
Thank you, Doc.
Okay. Now we write the anode, follow it by cathode by using two strokes. The two stroke is representing the salt bridge. Now the anode is the oxidation reaction. Now the oxidation reaction, you see, we move from reactant to product. So the reactant is written, then instead of using arrow, we use a stroke. That stroke represents the arrow. Then the cathode side reactant to the product, then the arrow is represented by that stroke. So basically what you are trying to say is that the anode electrode is being separated by interfaces. So from one phase, that's the reactant, to the product by one stroke, then the, from one electrolyte to the other, we use the salt bridge. That's the two stroke. And this is what we call the cell notation. The cell diagram has to do with you trying to draw this representation. And then the notation is just trying to do this. So when we see a cell notation, the meaning which we can read here is that there's electrons flowing from this part to this part. So this is the anode, and then this is the cathode. We can equally write it that way. Is that okay? Okay, so let me give an example then. So look at this reaction here. Okay, so now you can see we are using this Z rule to just represent this redox reaction going on here. Is that okay? So if I ask you to write the cell or just the cell notation, I think it's now showing. But then if we separate the half reaction, you're going to see that we're going to have silver moving to a silver plus moving to silver zero. Please, do you see that?
Yes, Doc.
And from plus to zero means that is what? Reduction. And so that is the cathode. That is the cathode couple. Now from zinc 0 to zinc plus, that is oxidation happening. And so that is the anode couples. So once I can identify the oxidation, which is the anode, and then the reduction, which is the cathode, I can simply write the cell notation or the cell diagram as the anode followed by the cathode, and then separate the anode with interface, that's the stroke. So that's the cathode also, and then the salt bridge between the two faces. Please, is that okay?
Yes, Doc.
Yes, sir.
Okay, so you within 1 minute, you try this. So class, if you can practice it, so try to write the cell notation for this. So write the cell diagram that has hydrogen electrode to your left, and then an ion electrode to your right. Include the salt bridge. So 2 minutes or 1 minute. Let me see if you can do that. Please, are you doing it?
Yes, Doc.
Doc, please, you said hydrogen and what?
Ion.
Oh, the question is there. Can't you see it?
It's not showing. There is the old screen that is on it.
Please confirm. And so the next time when you are coming, please get a nice phone.
I'm using.
Please confirm. You are using
No,
laptop.
please, it's showing.
And then your laptop will be Pentium 2.
It is showing, Doc.
So please, the question says that write down the diagram for a cell that has hydrogen electrode on your left, and then an ion electrode on your right. Include the salt bridge as well. So definitely, if I write the notation, you include the salt bridge. So let me bring my white background. We all do it together. Okay, maybe you are still looking at it. So okay.
That's okay.
Please, are you addressing me or you are doing the thing?
Look, I'm doing it and I was talking to myself. Thank you, sir. Zone of Proximal Development. Thank you.
You are talking to yourself.
Yes, yes. As I was doing it.
I hope you will not carry this into the exams. Otherwise, they'll say that you are cheating.
That I will not do it.
Yeah, any suggestion?
Doc, I have something here. It's H2 gas / 2H plus aqueous. Then double stroke. So
well, please. When you are writing cell diagrams, stoichiometry is not included.
All right.
So come again.
All right. Then H2 gas / H plus double slash Fe3 plus / Fe2 plus.
Okay. Is there so? Let me see if I can write. So, is there somebody having a different? And so H2 plus to H plus, the salt bridge to Fe2 3 plus, right?
Yes,
Fe3 plus. stroke the
Fe2 plus.
2 plus. Any different answer?
Yes,
so here the question was even straightforward by saying that on the left, on the right, if they could say that the hydrogen is the anode and then the ion is the cathode, without giving you what would be the electron loss in that thing. Yes, somebody mentioned my name. You want to say something?
Doc, I'm the one. I am thinking that since hydrogen is a gas, then there's a need for a platinum electrode on which the gas can operate. So mine will be H2 / H plus / PT double / Fe3 plus / Fe2 plus.
Please come again. I didn't get you.
So, look, I'm saying that since hydrogen is a gas, it needs a platinum electrode. So mine will be H2.
Look at what I've written. Is it correct?
Yes. Okay, Doc. I can hardly see it very well, but if it is PT, yes, then I'll agree.
A PT into bracket H2 / H plus double / and that kind of form. Now I'm just taking it.
Yes, Doc.
I get you. I just want to take it theoretically. Then we'll see in reality. So theoretically, hydrogen pushing to become. So we are assuming that we don't know that hydrogen is a gas, pushing to become H plus, and then that / to become that. Is that okay?
Yes, Doc. Yes, Doc. It's fine.
So now the point we are bringing out from what you just said is that we are not looking at, because it says that both electrodes are contacting the platinum. What means that both electrodes are so the platinum basically is just like the ion. Okay, I mean the wire. Now, basically, the platinum, again, is also a metal which can also be losing electron. And so, more or less, like the platinum is the one carrying the electron from the hydrogen gas to go and give it to the ion metal. So the hydrogen becomes charged, but then it goes through the platinum, because otherwise, then we should close the system. Otherwise, all the hydrogen will just, because it's a gas, it will just go away. But when we are not closing it, we put the platinum in here and then attach it to the ion. So the gas is generating or releasing electrons. But then it can't go through just like that. It has to go through the platinum, which then will be attached. So we can say that the platinum here is now assisting the hydrogen to be the anode. Please, does it make sense? Okay. So that's the...
Doc, if you can go over it again.
Okay. Now, this question is just an open question. It gives you the details, the clear details. And it reads that once you are going to be drawing the cell diagram, the hydrogen is on my left. That is my anode. And then my ion, from ion 3 plus to ion 2, will be on my right. That is the cathode. And include the salt break. That is the 2 strokes that we are going to be adding. Now, it gives you a detail something where it's going to tell you that the hydrogen, of course, in the question, if it ends there without telling you that the platinum is connected to the hydrogen, or both are connected, then theoretically we're going to write H2 stroke H plus double stroke Fe3 plus and then Fe2 plus. That's theory, in theory. But in reality, such a cell cannot work unless it is in an enclosed system, because the hydrogen which is going to be losing the electron is not in a solid form, neither is it in a liquid form. It's a gas which is in an electrolyte. And so it needs a carrier, and that is where the platinum comes in. So the platinum is inserted in the gas liquid solution, which is carrying the electron which the hydrogen gas is going to be releasing, so that it's going to be attach itself to the ion. So the platinum basically is just acting or just assisting the hydrogen gas to release the electron to the ion. That's why we don't, it's not the platinum which is going to release electrons. So we can write platinum to, or platinum stroke to platinum plus or platinum something. But then the platinum is just assisting. That's why I started with the theory, and I'm saying that hydrogen gas will be released. But now because the platinum is assisting, I've put the hydrogen into brackets, meaning the hydrogen gas is now being assisted by the platinum to release the electron and become hydrogen ion. And then that platinum again is connected to the ion, so that that electron which is being released will be carried to the ion. I don't know if I'm making sense.
So, Doc, so
yes.
Hello, Doc. So it's only the hydrogen that will be put into the bracket so that the platinum will be helping on the ion too.
So if I should get such a question, per the information that I have, well, I was just trying to explain step by step from the theory then to the application there. So such a question, how I'm going to address it is that I'm going to just write a platinum, because in considering cells, we don't consider gases. So I'm just going to say platinum to H plus. Then that H plus will then move the electron to the E, while as we move on, we'll be coming across much of these cells, the hydrogen cells. So we'll be using much of this. So this is how the answer or the solution should be like. And I'm trying to explain how we ended up with this one, not a hydrogen gas instead. So I put that into bracket to say that start from the theory, then give much addition to that. Is that okay? Yes. So that's is that it's not like the platinum is an electrode itself. No, it's just more or less like a connector. It's just connecting, helping the hydrogen to release that, but it's not going to be releasing electrons by itself. Well, that is it. On Friday, we'll start doing some few calculations where we're going to calculate the cell potentials and then the electromotive forces in the cell, and then a little bit. So these are still trying to deal with that. So the standard cell potentials, the electromotive, the EMFs, we'll just do some few calculations there by comparing to the series. And of course, we can continue from there as well, where we bring in the next equations and those stuff. Then we can now take, so this is the electrochemical cell. Time is fast spent, I can't come. So that I will now take the galvanic cell and deal with the various examples or kinds, like the primary cell, the secondary cell, then the fuel cell. Then I can move on to the electrolytic. So let's end it here. Friday, same time. We'll continue. Please, if you have a question, you can ask.
Hello, Doc. Hello, Doc.
Yes.
Doc, please, some of us,
yes,
we don't have the electrochemistry on our portal. We contacted Dr. Kofi to add it to our portal, and yet it's not yet done to us. So I don't know. When we are doing registration, we have 11 courses on.
Yeah. How many courses? 11.
Yes, Doc.
initially had 11. When we contacted, they said that was what we had to do, only to see electrochemistry. When we contacted Dr. Ado was telling us that yes, we have to do electrochemistry. So
With the chemistry,
we put
no, we'll put it this way. Put it this way. We all the chemistry major students, we are supposed to do the electrochemistry. What the Dr. Ado told us. Some of us, doc, we are not having it in our course registered or registered courses, like the chemistry major, biology minor students. We are not having it on our registered courses. It is only 11 courses, but the chemistry major, physics minor students were having it on their registered courses. But per the course code CHE, it means it will be an elective course for both of us. But when we contacted the doc at the department, they told us that these are the course that we've registered for, is the course that we are supposed to do. So and the electrochemistry wasn't part of us. But when getting the last week that Dr. Ado came by saying that we are all the chemistry students are supposed to do it. So my friend was trying to say
that's what happened.
So, Doc, as at now, it is not reflecting on our registered courses.
No problem. I think before your exams, this thing should be corrected.
Thank you, Doc.
It will be correct. Last year, too, I think the same thing. I think there's this miscommunication between science, the units there. They are not really communicating very well. And that's why, but then before your grade comes out, this and that's the same thing happened last year. So I thought they have learned it and then they are doing it this batch. But then we'll draw the attention again. But then it shouldn't be, once you take the course and you write the exams, your grade should reflect on your portal. And so it should be corrected before that. But you see, we are running the program with like 2 different departments. We are running it from the education, maths and science. And then we are running it from the other physical, like physics, chemistry, biology, and then maths. So 2 different departments running the same lesson. And we need to find spaces for that. Again, the idea for the program was more or less like a top-up. That's how I understood when they initiated. So they have teachers who wants to top up to become, say, from primary education to secondary. Is that not the case?
Yes, Doc.
Yes, Doc.
So the initial idea to me, as far as I remember, when they brought us together, was that they are going to be topping up. And you see, some of you have gone through the training college, you have diploma, and so the education courses, you did some of them in the colleges. So this time you should be topping up with the content. So this is more or less like content related. Then came the education again and says that no way, because the certificate is going to be a BEd certificate, they still want you to take the education courses again, even if you have taken them again. So it became a struggle between us, the content, and then the education distance. And eventually, because it is for them, they have succeeded in getting more of the education courses being pushed than the content. And that's why Dr. Ado is also fighting so that the content will be more than the education. But again, so we draw the attention, they'll bring it back. And of course, later you have to do more courses, take more education than the content stuff. So you draw the attention to, from here. I'll call the lady in charge and then draw the attention again, so that it should be correct. I don't think it's a problem.
So that's the reason why we the chemistry students, a little bit something, because the biology students, they are having 11, even 10, but we are having 12.
Okay. You are having 12.
Yes, though we are doing 12.
Yes, with electrochemistry we are having 12.
Okay.
But the biology students, the biology major students are doing 10. So we don't know how it is structured, but you keep quiet and suffer because we have nothing to say. Because when you complain, you keep on complaining. The last time I read this type of education courses, as we need the content. But one of the lectures, I don't know the person who answered me, said, if you've been doing the education course, then why should you worry on education? The moment you give you education, what exams, you should pass it and go. And I'm can you say such type of a thing? Because if you are requesting for a content and you are asking for education, that's the answer that you're supposed to give it to me. That if you give this education, far like you are saying, you have my knowledge in education, so you shouldn't worry.
I think that is all. If you have any question, then you can ask.
Okay, Doc. Thank you, Doc.
Okay, so see you on Friday.
Thank you.
Thank you, Doc.